Perfect.
Raj and Edis both came up with some ideas on how we could deal with this error that I created. I'm going to move forward with the idea of creating a Lambda function to go through the column and replace the ends with nans. So what we can do is, if we just wanted to do it within the race known column, let's just create a copy of that race known column. So df, actually should I start? I need to go back to the original data frame so it's not corrupted anymore. So I'm going to just assign it back to df original. Now we've overwritten all that bad work we did before. So now what we have here for those, just as a recap, we've just loaded the data set from Austin, Texas on police stops. And so we've got in here this should be the first command you run in most cases on most data sets, just to get a feel for what's in it. And this could have helped me avoid some of the misunderstandings that I had early on. But now I'm going to create a race known. I'm going to create my own column. With nans. First step is just going to be taking the original one and just copying it.
Hobson, I think you forgot an equal sign.
Excellent. That's the kind of help I need. Catching me before I make mistakes. Thank you. So we've got, so now we've created a new column. We can do that df describe again, see that column, see that its statistics are still the same as the original one. So race known, 11,000, 11,000, so we're good to go. Now we can modify that without having to worry. We're going to use another advantage of using underscores and proper variable names is you can use tab completion and it happens a lot faster. And you can use the dotted syntax if you like. So next thing we're going to do is we're going to do a dot apply, a function that has yet to be created. And we're not going to use a def. We're going to use, which is the normal way to create a function in Python. Does anybody know what I'm about to do here? Does anybody have any ideas how you can create a function without giving it a name and without using def?
Lambda function.
You got it. So we're going to create a lambda. And what this lambda function takes as an input is the first argument, unlike normal functions where that comes after parentheses. In a lambda function, that's the variable you define first, almost always in a lambda function, because these are unnamed functions that only have typically a single argument. We usually call that just x. Put a colon after that, and then everything after the colon is what you want to return. So if you're just doing a single mathematical equation, lambda functions are great. It's creating what's called an unnamed function, or a lambda function. So what we want to do to that x, which is either a y or an n, is we want to return a nan, np.nan, if x equals, quote, is it race known or race unknown? It's race unknown. So we want race known. So we want to say, we want to create nans for x equals n. Else, this is another trick. You can do if statements on the same line. So you can create, as long as it's just an if else, then you can do an if statement based on any condition. And we're going to return the x value if it is equal to y. Oops, we don't want to return if race is equal to known. Oh yeah, so we're going to return np.nan if the race known is equal to not n, and otherwise, and I should use my guidelines, race known. So this is more readable and I don't have to second guess my logic. So if race known is no, then we are going to return nan. If race known is Y or anything else, then we're going to return race known, whatever that character is. I guess that'll do. And that's going to, I'm not assigning that to a variable at the moment, so that's just going to go out into the ether. Unless I do, so that just created a bunch of nans in that column. We could do something like is null sum. Is null will catch both blanks as well as nans. So that does have a lot more nans in it, but it doesn't completely fill it with nans. So far so good. So now I think we're probably ready to assign it to an actual column. We can actually assign it back to that original, what do we want to assign it to? I think I'll probably, well, let's just create a new one. Oh, we could use the old one. That's the one that already existed there. There's another way I could do this. So this is the way to reassign it back to the same column where it got its data. I think that will work just fine without any of these copy errors. We don't have to create a copy or anything. Another thing we could have done is we could have done it this way. Within that apply function, I think we can say in place. I'm gonna hit tab and see if it comes up. No, it doesn't. I'm gonna try in place, see if that tab completes. No, it doesn't. So I'm wrong. But I thought we could say in place equals true and it would do it on the column already. Maybe I should use the quoted square bracket syntax. Doing it to a dot attribute, doing an assignment to a dotted attribute is really dangerous. In fact, I think you should never, ever, ever do it because in Python syntax overrides Pandas syntax in that case, because it's actually creating a new attribute that may not have all the properties of the old attribute of that object. So that gets deep into Python coding for object-oriented classes, but this is the right way to do an assignment. And so I'm going to do it also on this non-assignment with this apply in place equals true, just in case it works. It doesn't work because that didn't tab complete, so that's not an argument. But many functions in Python and in Pandas have an in place equals true that allow it to happen within the data frame without it creating a copy of it in a new column or copying it back to even the old column. Anyway, so we're all good now. I think we've got a df.describe that's getting closer to the practice data frame that I wanted us to work with. Another thing we can do to make this describe, we could have changed that y into a 1. Let's do that again as well. Now that I know it's working, make sure tab completion is working so I spelled everything correctly. Good. Get rid of the in place. And then let's take this, and instead of returning race known, let's return a 1. This will allow that to become a floating point column so that when describe does it on the numerical columns, it'll show up among the numerical columns. So it's no longer a non-numerical column. And just to keep track of everything we've done, so this is going to replace all those Y's with 1s.
This is replacing ends with 1s.
No, I think because if race known equals in, that's going to return nan. So you can read this like an English statement. It's going to return np.nan if race known is in.
Oh, right. I see. Yeah.
And so this should hopefully work for the Y's. But you're right. It's not just Y's. It's also anything else that exists in that data frame and for that value. So now let's do a df.describe. And all of that was just to get rid of the include equals all and still have our column show up in this list of statistics. Great. So we've got a mean of 1. So, race known. That surprises me. Oh, because the nans. So when you calculate a mean, nans are ignored. They're not considered to be zeros. So, so this makes sense. So what we have is race known is Y. We've got 11,000. Oh, yeah, okay. So that's, oh no. I'm thinking back to those value counts and those ratios we got, and I can't quite fathom why the race known is still has a bunch of race characters in the race column. Anyway, let's do a linear regression. Let's get this done. We've got about another 30 minutes. So we're gonna import first. Let's just make sure we've got scikit-learn installed. sklearn. Great. It looks like it's working. From sklearn.linear model import. There's a lot of really good linear regressions. I'm going to use the most basic one. It's this basically ordinary least squares regression that only runs through your data once and gives you the perfect fit to the data. It's the perfect in the sense that it uses it has all the coefficients that make the line up perfectly with your variable. We're going to do a single variable linear regression since that's probably most familiar to you. And we're going to create an X variable that is race known. That race known column with nans. Oh, we're going to do a fill note on that race known with nans. Let's do that exercise first. So df dot race known with nans. I need to do the. I'm not going to do a fill nut just yet. I'm going to do an isna, and we're going to create a new column. So I'm going to create was equals and or I'd say isna because that's valid Python. That's a valid Python code function isna. So I'm going to name my variable that, and then assign that to that exact expression to make it race. Just so you known with nans isna dot isna. So, but I want to do tilde isna because I want the nans to show up as zeros rather than as ones, since we already have the ones filling in for the y's, I think. So I'm going to say not isna. So this is what I asked Edis to do on the Condarp data set. So that's the only reason I'm showing this is that it's not useful in this particular case. Oh, I just created a list. That didn't help. Great. So our isna, not isna column didn't show up. And wonder why they didn't end up being like maybe because it's trues and falses at this point. Let's just see what's in it. It's trues and falses. It's Boolean. And it has 11,000, so they're all true. Wow. So I've messed that up royally. Maybe I should have done isna instead without the not. Wow. Well, now you can see how it's hard even for people who supposedly know what they're doing to get data cleaning correct. Where's my sum? df dot is sum. Wow. So my race known with nans got cleaned up by that non-copy operation that I did. Again, I somehow hosed it up. Anyway, let's move on to actually creating a valid model. But in what we'd like to do successfully, or Edis's goal is for every column that contains nans or missing values, is null, is true. We'd like to create a copy of that column that contains zeros or ones or trues or falses for the presence or absence of nans. And it doesn't matter the polarity, whether you have trues and falses, as long as you have the trues associated with one ISNA and falses associated with the other. That's
So it would be a column with a true statement every time there is a value, and a false every time there's not a value.
correct, but it's okay if it's just the opposite of that.
Okay.
So if it's false, whenever there is,
I see.
because the model will figure that it'll do the slope in either positive or negative to deal with whatever that value is, because it's going to convert it to a 0 or a 1, and then it's just going to have a slope like any other linear regression. And that's, as I do this linear regression, it'll be more clear how that's all working. So I think I've imported the linear regression. Yep. So we can create one. And I'm going to call that the generic word model. Normally we don't use generic words, but because we're going to be creating a lot of different models of different kinds, I want to use that so that I can reuse the code. And it can be part of either a function or a for loop where we're training many models and trying very many different approaches. That's what's called hyperparameter optimization. So let's just give it a generic model name rather than calling it LR or something for linear regression. And now we're going to, and just so you see what that looks like, what some of the arguments are that we could have called to set that up. We could have, there's only really a couple hyperparameters for linear regression because it's that most basic one. We could either fit the intercept or not, or assume that it's 0, essentially. We can also normalize the data set when it's going in. Normalize just means making sure that they range between 0 and 1, or it could be standardizing it, making it have a standard deviation of 1. But I'm pretty sure it's ranging it between 0 and 1. And so before it goes into the fit, we're not going to use that. So we're just going to use the raw data so you can understand what the coefficients mean. Let's just pick a column that we want to predict. So let's look at, let's try to predict a race origin code. And so we're going to say X equals that data frame. And we're going to put a list inside of here. Like before, remember we had a list of things, an array of trues and falses that went inside the square brackets. We're going to create a list of lists. I mean, a list of strings. And that's how that list, because we want this to be a data frame rather than just a single, we want it to be a single column data frame rather than a single series, which was what would happen if I just used a single square bracket. That syntax is a little tricky for people to,
Shouldn't it be Y? Because we are predicting that. Like,
as
per the normal.
Yeah, yes. You're right.
Yeah.
Thank you. And tab completion is not working for me, so I'm a little concerned. Oh, because I used double square bracket probably. So this one, it's okay to use single square brackets because we are trying to create a single series, a single array. That's why we use the lowercase y, as Raj pointed out. For X, the race known column is the one we want to use. And in this case, we're going to allow the option of having many other columns. So we're going to create a list of lists. And it doesn't do tab completion as soon as you do the double square bracket thing. So I just have to type it out and try to get it correct. It looks pretty race known. That'll work. Let's just display the head. Y doesn't have a head, I don't think, because it's a series. Oh, it does. Great. But it shows you it's a series by giving a slightly different representation of it coming out. Now let's see if we can do a fit. So we're going to say model.fit. You don't have to, this, I liked, in the past we had to do this, reassign it back to itself. But now, from now, in the most recent versions of scikit-learn, it's doing the fit in place. So you don't technically have to do that assignment. But we're going to do, yes.
Aren't we predicting a categorical variable? So wouldn't we need to use a logistic?
Yes.
Regression?
That would be a much better model than the one that I'm creating. But all that does is choose a different transformation of our data before it does a linear regression. So even so, it would be a better fit because our line that we're creating is going to go past that categorical variable.
Right.
And actually, now that I think about it, this race origin code is categorical, and we're not even turning it into zeros and ones. So we're not even ready to do a fit to the model to this yet at all. Very good catch. So we need to do that first. So I'm going to teach you another really handy function in Pandas, unless you already know it. Does anybody know what you do with a categorical variable?
Get dummies. Get dummies.
Got it.
Get underscore.
You got it. Thank you, Raj.
Yeah.
So we put the data frame in as our data set. We can do that to the entire data frame, and it will find all the categorical variables, anything that's an object, anything that's, actually, it may not work on the things that are integers that should be data frame, should be considered to be dummy variables or categorical variables. We'll see what it does. May have to reload it and clean our data set again. If
I think you might have to drop one of the columns.
Yeah. I'm trying to cancel it out because those columns, maybe I'll just selectively do it to only columns equals, and I'll give it just a list of the one column we want to work on rather than trying to do it to the whole thing. Because like the things like the ID or strings that are unique throughout the data frame it would turn our tall data frame into a square data frame that would take up massive amounts of RAM. Okay, so the columns that we want to do get dummies on are race, origin, code. It's not completing for me. Hopefully it didn't overwrite that data frame. I think that will work. And I'll just okay, cool. This still has all the other columns. It's just added an additional column for all the different races that exist and putting a 0 and 1. So that first, so for instance, race origin code H, it means that on the second row, we must have had race origin being equal to H. It doesn't actually show the original column. I think it got rid of it. Race origin code, it starts with race origin code A. It doesn't have the original race origin code. So we can't double check it. So we have to just trust that it did that correctly. I think in the original head, we did see H as being in the second row.
Can't you also drop one of those? Because if you know all of them, then you'll also know the last column.
That's another option within this function. We can say drop first, and that will drop one of them if we want to automatically. I don't like to do that because that skews the results and it makes the interpretation of the coefficients a little more difficult. Mm-hmm. This way, it will balance the coefficients across all the races appropriately. Yes, there's redundant information. Yes, there's collinearity between these variables and each other, but it's more useful on the back side if we don't do that. So I decided not to do. Now we can finally do the regression, but it's a multi-target regression rather than a. Let's do it the other way around. Let's make this a this is actually going to be a very bad model because it only has a single categorical variable as all of its input features, but at least it's a multivariate one. We've got 10 minutes left, so I better move fast. X equals, let me go back up to my previous X. X equals race known. So I'm going to swap our target variable and our feature variables. So in this one, I'm going to make our features equal to C for C in df dot columns. Oh, we need to use the cleaned one. If C starts with race origin. What this does, this is a list comprehension that goes through all of the elements of the columns names. Columns represents the column names, which are strings. And so we're doing a for loop through them. And we're going to return or include as an element in this list the raw column name, but only if the statement at the end of the list comprehension is true. So it'll only happen when it starts with, hopefully this will work, and create us an X data frame that contains what we want as our features. X.head, we're good to go. So that's our features. Now let's do our Y, and we're going to do it the wrong way, as Raj pointed out. We're making our target variable the race known code. Turns out the linear models are equivalent. The slopes will just be in the opposite directions, and we can still get the same kind of information we want out of it. So we're going to say y equals df cleaned, and we're going to choose just a single column in this case, and this is going to be race. No, we're not going to use the race known with nans because I think we've corrupted that. We're just going to use the original race known and hope that it has not been corrupted. We should probably double check that in a second. So we're trying to predict that race known character. So we're going to try to see if there's a causal, a correlation or pattern between whether the race origin is known in the past based on when the arrest happens, what the race origin code is recorded in the database. So now let's do model.fit x comma y. We're not doing train test split, which is what you will want to do in the future on all your real world models. You want to have a separate test set that's reserved for checking the accuracy of your model. We won't be able to know how good this model is, but it's going to be a really poor model anyway, so it doesn't matter. Oh, great! We haven't dealt with our target variables being y's and n's, so we need to do that. So y equals y dot apply lambda. Actually, I think I can do it quite easily with just y equals y. Since I'm not, hopefully I don't think I'm affecting the original data frame. So hopefully this should be a bit better. So now this is trues and falses. We can do as type int if we want. Let me just look at the first few elements of that, make sure that worked. So type bool. So now we changed y's to true and n's to falses. Next, I want to do, let's make sure that that's great. There's only 3,000 trues in the race known column. That's what it was originally, I think, in the original data set. Next, let's do So I think we can go, that can go straight into a model because it knows how to convert trues and falses into zeros and ones. We could also say y equals y dot as type int or float or whatever we wanted, and that would work as well. But I'm gonna go ahead and just show you that it does work. Model dot fit x comma y. So now let's see how well it did. Model dot score x comma y. We're using our test set and our training set as the same thing, so we can just plug them both in. Got really low accuracy, really low correlation between our predictions and the truth. Mostly because we have very sparse information about the problem, and our target variable is very rarely true. It's very imbalanced, for one thing. If we did a logistic regression, this would come up with like 96% accuracy simply by, and this isn't, and score is the correlation coefficient between our predictions and our accuracy. Let me show you one last thing that's really important in terms of the basics of modeling. You want to know how to do something like root mean square error or the actual accuracy. So let's do that. Let's say model dot predict using X only. So these we'll call Y pred for Y predictions. And then we'll find out the number of times that our Y pred equals Y. And this will tell us how many times we got it correct. And we got it correct no times. I think because those are two different variable types. So I think I probably need to say as type int. Oh, we did a floating point. We didn't do a classifier. We did a linear regression. So it's never going to exactly equal it.
Yeah.
What you do is we'll treat it like a linear regression by doing that as type int. And so this is the error. So I'm going to give you the formula for root mean square error. So this is the error. And then we're going to say the square error. So RMSE equals E squared mean and then square root. %, error. Doesn't sound too bad when we're trying to hit zeros and ones, but I bet that slope on the model is very low. I bet it's basically predicting zeros all the time. Let's see. Model.coef. So this gives us the coefficients for each of our different race categories. And we can see this is where we actually want to get our information. Even though our model accuracy is very low, it gives us information about the statistics about which of those are correlated with which. So let's assign these. Let's make a series out of this so that we can assign those to the actual column names in our X. So let's say pd.series. We're going to give it an index that contains those column names. So that will be in df clean. Oh, we need to do, I think it's in x.columns. I think that will work. Great. So now we can see which codes are associated with positive and negative correlation with the target variable, which is in this case race unknown. So we can see that that W1 is close to 0. It's less than 1%. It's 0.1% positive. So that means that let's make sure that we have the polarity of this thing. What's the Y polarity? How do we create Y? So Y was when Y was 1 when Y was equal to, so race known, so the race was known. So when race is known, there's a positive correlation with white, a very weak one. When race was known, there is a negative correlation with whatever this race code O means, and so on. We got a really significant positive correlation with 1.1% positive slope on race code B, and so on. So this is how you interpret a model once you're done creating it, and this is going to be the key to your work at us. And and Jake on the linear regression you're creating for the CANDARP data set. We're going to go through each of those coefficients and think about and talk about what they all mean in terms of what's causing anemia in India in that CANDARP data set. For this case, we would have to spend some time talking to the people who created this data, reading up the documentation, reading some of the reports, and trying to figure out what this actually means in the real world. And like Etta suggested, we'd probably use a logistic regression to get the accuracy up and get better information about exactly what the correlation was between these variables and the target. Plus, we would add additional feature variables. Let's see if we can do one of the numerical features and just do that